Alright guys, well, we're missing our second day of school, so I figured if I'm going to be home for 2 days, I can help you guys out by making some videos to help with finals review. This video here is going to help you with some of the topics from first quarter. One of the first things we talked about was what it means to be a coterminal angle. And these are angles that have the same ending point. So if you visualize our unit circle, if an angle is drawn here, it could have just been, for example, 30 degrees, or you could have gone all the way around the circle once and then again, making it 390 degrees. You could have also gone backwards around the circle and gone negative 300 degrees. So when you're asked to find coterminal angles, what you want to do is you want to add or subtract 360 degrees or 2 pi if you are in radians until you get an angle that is in between 0 to 360 or 0 to 2 pi. In these two examples, this would be 60 degrees and this would be 304 degrees. Here we would add 360, here we would subtract 360 2 times. As far as operations on angles, you need to be able to work within degrees, minutes, seconds, decimal degrees, and radians. If we ask you to add and subtract angles that are in degrees, minutes, seconds, you want to think kind of like terms and line them up. So for example, on problem number 1, I would line these two angles up and I would add. Now when I add this, I end up getting 78 minutes and 90 degrees. However, we know that every 60 minutes is equal to 1 degree. So we're going to carry, and we're going to cash in 60 minutes into 1 degree. So our final answer is 91 degrees and 18 minutes. When we do subtraction, if I don't happen to have enough minutes, I need to borrow. So I'm going to borrow 1 degree and turn it into 60 minutes. So 60 plus 15 gives me 75 minutes. And now I go ahead and subtract. And I will get 55 degrees and 47 minutes. Now when we're converting decimal degrees into degrees, minutes, seconds, we have to take this decimal portion and multiply it by 60. So if I take 621 and times it by 60, that gives me 37.26. The whole number part is the number of minutes. Now I take that remaining decimal and times it by 60 again to get the number of seconds. That gives me 15.6, and then you either take the 15 or you can round up to 16. I imagine that the answer choices will probably have you round up. So our answer will be 45 degrees, 37 minutes, and 15 seconds. And using some common sense, this should make sense because 0.6 of a degree is a little more than half, and 37 minutes is a little more than half of 60. To go the other way, we have to take 41 and divide it by 60, and the 16 seconds and divide it by 3600. And we add both of those decimals to 125. Our final answer here should be 125.688 degrees. Here are our basic trig functions. You should know these by heart at this point. Remember that sine and cosine are never undefined, and the other 4 functions can be undefined when their denominators are 0. As far as our quadrantal angles in period 7, this is for you. I promise I taught you this. I took this right off of our notes. This is not a made-up word. When we're dealing with quadrantal angles, I suggest that you draw a quick graph and then just locate which one of the quadrant lines the angle is on. Our answer is always going to be either 0, 1, -1, or undefined. And for all of these angles, r is going to equal 1, and x and y equal 1 or 0. So if we were doing the secant of 270 degrees, that would be down here. And secant is going to be r over x, and at 270, r is 1, x is 0, so this is undefined. If I were doing the cotangent of 0, cotangent is x over y, so I have 1 over 0, again, undefined. And if I was doing cosecant at 90, cosecant is r over y, 1 over 1, and so this is equal to 1. Ranges of our trig functions. Remember that the input, or the domain, for all trig functions is an angle. Sorry, this is so sloppy. The range, or the output, is a ratio. And we've talked extensively about how sine and cosine live in between -1 and 1. If you recall, I've drawn this graph many times in class. And secant and cosecant are on the outsides, meaning that they must be greater than 1 or less than -1. And tangent and cotangent, they're the wild child. They can do anything they want. It's kind of like my son. He is bonkers. So that's where our different functions are at. As far as how we would expect you to use this, we might give you something, for example, and say on a no calculator portion, sine of theta equals, 1.72. And I would expect you to know that this is false because sine can never have a ratio greater than 1. Alright, if we give you a problem like this, and we've done this quite a bit, where we want you to find one function, we're giving you another function, and we're telling you the quadrant. The whole value of knowing the quadrant is we know the positive or negativeness of x and y. The easiest way to approach this problem is to use the given information to solve for your x, y, r. So if I look at what I'm given, cotangent's x over y, I have root 5 over and 6 for my x and my y values. Using Pythagorean theorem, I can solve for my r value. So 5 plus 36 equals 41, therefore r equals square root 41. Remember, r is always positive, x and y are both negative because we're in quadrant 3. So now I'm asked to find sine, which is y over r, and my answer will be -6 over root 41, which we will rationalize to get -6 root 41 over 41. You can also solve these problems using identities. However, the x-y-r was a preferred method for students, and the final is multiple choice, so it really doesn't matter. Cofunctions can be used to rewrite one function in terms of another. Sine goes with cosine, tangent goes with cotangent, and secant goes with cosecant. Imagine that. Properties of our cofunctions is that the two angles are always complementary. So for example, if I had sine of 40 degrees, that would be equal to cosine of 50 degrees. So two cofunctions are only equal if their angles are complementary. What you see down here are the cofunction identities. Each pair has two different formats, one in terms of sine, the other in terms of cosine, for example. And these are also true for radians. If I were to write tangent of A equals cotangent of pi halves minus A, that's how I would write this in terms of radians. Remember that the angle has to come first. If it were written as A minus pi halves, then the angles would not add to equal 90, so that is incorrect. Reference angles is another topic we've talked about quite a bit. This notation right here with the angle with the apostrophe mark is the symbol for reference angle. If the angle is already in quadrant 1, then that is the reference angle. The reference angle needs to be a positive acute angle. It is always the angle that is made with the x-axis. So if we are in quadrant 2, we would take 180 and subtract the angle. If we're in quadrant 3, we would take the angle and subtract 180. And if we were in quadrant 4, we would take 360 and subtract the angle. This is also true for pi or 2 pi if we were dealing with radians. Unit circle. Oh, don't forget, we need to know this inside and outside. The unit circle is based off of two of our special right triangles, the 30, 60, 90, and the, that's totally not to scale, but 45, 45, 90 triangle. And you can either have it memorized or you can use the special rules for the side lengths. We should by now know this by heart. When we are entering things in our calculator, things to remember are how to type this stuff in. So for the first one, we would type in cosine of 121 plus 45 divided by 60 plus 23 divided by 3600. Correct answer should be negative 0.526. For the second one, tangent, this should be 0.443. Make sure we are in the correct mode. If you see this little R superscript, that's just a reminder that we are in radians mode. Now, to type in the secant one, we have to use our reciprocal function. So let's remember our reciprocal identity. Reciprocal identity says that secant of theta is equal to 1 divided by its reciprocal cosine of theta. So to type this in, I'm going to type in 1 divided by cosine of 1.6 and make sure that I'm in radians. And that will give me 34.247. Now this bottom section, these little negative ones, means that you are doing the inverse function. Another way that we will see this written would be, for example, arctan is the same as if I were to have written tan inverse. Alright, so when I type this in, for most calculators you have to type secant sine and then the 5 divided by 6. Again, we should be able to do this stuff no problem. We have been doing this all semester, which is one of the nice things about this final. It's very cumulative. To type in the cosecant, secant, and cotan inverses, unless you have an 89, you have to remember how to type this in. So you are going to use the reciprocal inverse of the reciprocal. So I'm going to type this in. The reciprocal function is sine, so I will say sine inverse of, and then I have to do the reciprocal. And the reason why we're doing this is because the 4.676 is a ratio. Alright? Sine can never have a ratio equal to 4.6. However, the reciprocal is a valid ratio for sine. So we have to do the reciprocal to get a possible sine ratio, then do sine inverse. Alright. After we mastered everything in degrees, we switched into radians. Remember the rules for how to remember the different numerators. In quadrant 1, all of your numerators are equal to 1. In quadrant 2, all of your numerators are 1 less than your denominator. In quadrant 3, all of your numerators are 1 more than your denominator, and in quadrant 4, all of your numerators are 1 less than double your denominator. As far as our reference angles, just remember that the 6 goes with the 30, the 4 goes with the 45, and the 3 goes with the 60. The 2 is on the quadrants. Alright, converting between degrees and radians. We should be able to do this with or without a calculator. I'm just going to go through how to do this without a calculator, since this will be on the no calculator portion of our final. Remember that the ratio to convert is pi to 180. Whichever unit you want to finish with is the unit you need to have in the numerator. So here, since I want to finish with radians, I'm going to make sure that I have the pi in the numerator. In the second example, I want my answer to be in degrees, so I'm going to make sure that I have the degrees in the numerator. Now when I go ahead and multiply these, remember some basic rules. For example, I can knock off the zeros, and then I just have 22 over 18. Those are both even. Divide by 2, 11 pi over 9 radians. Over here, I can knock off my pi's. I know that 9 goes into 180 20 times, so now it's just 4 times 20 to give me 80 degrees. Alright, arc length and area of a sector. Remember these formulas. S equals r theta. The biggie that we have to remember is that theta has to be the angle in radians. So in this first problem, my angle is already in radians, so all I am doing is simply multiplying 18.2 times 3 pi over 8, and the answer is already down here. In the second one, I have to convert this 210 into radians first. Check your answers right there. For area of a sector, Same thing as arc length. The angle has to be in radians. So if we look at this first one, we'll say the area equals 1/2 2.6 squared times 5 pi thirds. For the second one, 1/2 5 squared 120 times pi over 180. And our answers are 17.698. And this one over here I have exact because I would imagine that that would be on a no calculator portion. Remember, units for area of a sector are square units, and units for arc length are linear units without the square. Alright, now let's talk graphing. Whew, this was a huge chapter. When we graph our functions, there's several things to look for. First of all, we have to factor out the coefficient on x, which is the b value. If the b value is already factored out, great. If it's not, we have to factor it out. And to find the period, we're going to do 2 pi divided by b. This is true for sine, cosine, secant, and cosecant graphs. Then, to get the phase shift is going to be d. Remember that we have to think the opposite. The formula includes a minus. So if we see, for example, x minus pi halves, that's actually moving to the right. Your vertical shift is going to be whatever number is added outside the function. Amplitude is our a value. Now, remember that amplitude is technically the absolute value of a. It is always positive. If the a is negative, then the graph flips. It does a reflection. When we label our vertical axes, we are going to start with our vertical phase shift, and then from there, we will go up and down the amount of the amplitude. For our horizontal axes, we start at our phase shift, and then we take our period and divide it by 4, and this will give you your scale. You take this scale amount and you add it 4 times to the starting phase shift to label your axes. Your axes needs to have 5 points. Remember those key points were 0, 1, 0, negative 1, 0 for sine, and 1, 0, negative 1, 0, 1 for cosine. If your amplitude is anything other than 1, then these actually turn into, you can almost think of it like this, a values instead of 1s. So here's a problem that we are going to graph together. First of all, I want to notice that I need to factor out my b. So this would actually be 3 times the cosine of 2 times x plus, and when I divide a 2 out, this actually becomes pi fourths. If I were to distribute that 2 back in, I would get pi halves. That's how I know I did this correctly. To find the period, I'm going to do 2 pi and divide it by my b value of 2, which gives me pi. Therefore, to get my scale, I take pi and divide it by 4. I get a scale of pi fourths. My phase shift is going to be left pi fourths, and it's left because I see a plus sign here. My vertical shift is going to be up 1, and my amplitude is going to equal 3. Alright, when I go to graph this, I'll start with my up 1 for my vertical shift, and then since my amplitude is 3, my vertical scale goes from 4 to negative 2. Now, horizontally, I've got a pi fourths shift to the left, and now since my scale is to keep adding pi fourths, my next point will be at 0, then at pi fourths, 2 pi fourths or pi halves, and 3 pi fourths. Now I'm going to go ahead and put a dotted line at my vertical phase shift. Some people find it helpful to put dotted lines at your max and your min value as well. Do whatever works for you. Remember, the final is multiple choice. You just have to be able to recognize the correct graph. Since this is cosine, cosine is the 1, 0, negative 1, 0, 1, and that means I will start up at my maxima. So 1, 0, negative 1, 0, 1, and then I just sketch my curve through the points. Now chances are on the final your graphs might look more like this because remember our graphs are periodic. That is okay. Look for the section of the graph that you would have done and match that up. Other things that we could ask you about our graphs, we can talk about a maximum or minimum value. My maximum value is 4. My minimum value is at -2. If I asked you to find the ordered pair at a certain x value, you would just plug that x value in and evaluate to get the y value. Sine and cosine graphs are never undefined. I could ask you about the range of this graph. The range is basically all the values, the y values. So the range here, the smallest is -2, the greatest is 4. And we do use brackets because those points are able to happen at -2 and 4. Now for graphing secant and cosecant graphs, these we're basically going to graph the corresponding sine or cosine, and then it's kind of going to look like a mirror image graph. We will have vertical asymptotes where we would have had x-intercepts, and the domain is going to be everything except the vertical asymptotes, and the range is going to be everything except the range of the cosine and sine graph. What you'll see right here is a basic graph for our sine function. The reciprocal of sine is cosecant. So if I wanted to graph my cosecant graph, then anywhere where I have an x-intercept, I would have a vertical asymptote. Since these are my x-intercepts, remember those are the values where I have a 0, then I'm going to put a vertical asymptote here. And then when I sketch my graph is basically going to almost think of it like, they kind of look like little parabolas. From the max and the min values is how my graph is going to look. And remember, just like how my sine and my cosine graph repeats, so does this one. The range for this graph would be from -infinity to -1 inclusive, and 1 to infinity. The domain for this graph, cosecant, is undefined at 0, pi, 2 pi, etc. So the domain will be all x values except when x is a multiple of pi. Make sure you know how to do the range. The domain is more of an extra credit type topic. As far as tangent and cotangent, these are very similar to the other 4. However, the period is only pi instead of 2 pi. So when we find the length of the period, you do pi divided by b, not 2 pi. To get the scale, you still take the period and divide by 4. That has not changed. If we compare these two graphs of tangent and cotangent, you'll notice that our tangent graph is centered about the origin. It has key points at -1, 0, 1. So if this is my a value, in this case we're just going to say it's 1. The first point would be at -pi force -1, 0, 0, pi force 1, and I would have a little squiggle that goes through those points. The graph begins and ends with asymptotes. My cotangent graph has a pattern of 1, 0, -1, and those points would look like this. And then we would draw our squiggle through it. So as far as similarities and differences, they both begin and end with an asymptote. They look like they are reflections of each other. As far as how to remember which one has the +1 or the -1, just think about the angle measure. The tangent graph starts at -pi force, which is in quadrant 4, and tangent's negative there. The cotangent graph starts at pi force, which is in quadrant 1, and cotangent's positive. So that can help you remember which one goes where.